Section: Physics IQ Benchmark. In this section, we describe our efforts to create a dataset called Physics IQ, aimed at evaluating how well video generative models understand various physical laws, including solid mechanics, fluid dynamics, optics, thermodynamics, and magnetism. Our dataset consists of 396 videos, each lasting 8 seconds, which depict 66 distinct physical scenarios. Each scenario is designed to test a model's grasp of specific physical events, such as collisions, object continuity, and the behavior of fluids, among others. We filmed each scenario at 30 frames per second with a high resolution of 3840 by 2160 pixels, using 3 camera angles: left, center, and right. Each scenario was recorded twice to capture the natural variability found in real-world interactions, which we refer to as physical variance. This results in a total of 396 videos, all shot from a static camera without any movement. To evaluate physical understanding, we split each 8-second video into a 3-second conditioning video and a 5-second test video. The conditioning video serves as a prompt for the model, while the test video represents the expected continuation of the event. We carefully select a key frame from the conditioning video to ensure that predicting the continuation requires some understanding of physics. We also allow models to use human-written text descriptions as additional context, without revealing the outcome. Notably, stable video diffusion is the only model in our study that does not accept text as a conditioning signal. We created the Physics IQ dataset to address the limitations of existing benchmarks, which often rely on synthetic data. By providing real-world videos that capture complex physical phenomena, we aim to offer a more rigorous framework for assessing the capabilities of video generative models in understanding physical principles. Section Summary. In this section, we introduce the Physics IQ dataset, consisting of 396 high-quality videos that test video generative models on various physical laws through diverse scenarios, filmed from multiple perspectives. We also outline our evaluation protocol, which challenges models to predict the continuation of physically interesting events, emphasizing the need for true understanding of physics rather than mere pattern recognition. Section: Models. In this section, we evaluate 8 different video generative models using our benchmark. The models we assess include VideoPoet, both image-to-video and multiframe; Lumiere, image-to-video and multiframe; Runway Gen 3, image-to-video; Pika 1.0, image-to-video; Stable Video Diffusion, image-to-video; and Sora, image-to-video. We acknowledge that Luma and VO2 are 2 other well-known models not included in our benchmark due to Luma Labs' usage policy and VO2's unavailability at the time of our study. Each model has specific requirements for input conditions, single frame, multi-frame, or text, frame rates, ranging from 8 to 30 frames per second, and resolution, between 256 by 256 and 1280 by 768 pixels. We ensure that the input conditions, frame rates, and resolution match the model's preferences by preprocessing the Physics IQ videos. Among the models we studied, only VideoPoet and Lumiere can accept multiple frames as input. These models also feature a super resolution stage, where they first create a lower resolution video and then upscale it. However, we found that the lower resolution outputs were sufficient for testing physical realism, so we skipped the super resolution step. Our benchmark focuses on physical interactions, where having temporal information is crucial, leading us to expect that multi-frame models should generally perform better than image-to-video models. For evaluating physical understanding, we use metrics that assess the visual quality and realism of the generated videos, such as peak signal-to-noise ratio, structural similarity index measure, Frechet video distance, and learned perceptual image patch similarity. While these metrics are effective for comparing visual aspects, they do not evaluate a model's grasp of physical laws. For example, PSNR and SSIM focus on pixel similarities but overlook the accuracy of motion and interactions, while FVD assesses overall features without penalizing physically implausible actions. LPIPS emphasizes human perception rather than physical accuracy. To measure physical understanding in our benchmark, we employ 4 specific metrics. 1. Spatial IOU, which identifies where actions occur. 2. Spatiotemporal IOU, which determines where and when actions happen. 3. Weighted spatial IOU, which assesses where and how much action occurs. 4. Mean squared error, which evaluates how actions happen. We combine these metrics into a single score, the Physics IQ score, by summing the individual scores, applying a negative sign for the mean squared error since lower values are better. This score is normalized so that the maximum expected physical variance is set at 100%. For the spatial IOU metric, we focus on the location of movement as a key indicator of physical correctness. For example, in a scenario where a duck interrupts a domino chain, only the dominoes to the right of the duck should fall. We compare generated videos to ground truth to see if the movement locations align. Since our benchmark videos are filmed from a static viewpoint, we can easily identify movement by analyzing pixel intensity changes across frames. This results in a binary motion mask video that highlights motion regions over time. We then create a spatial motion map by collapsing these masks across time, marking locations of action with a 1 and non-action with a 0. We compare this motion map to the one from the real video using intersection over union, which measures the overlap while penalizing discrepancies. This allows us to assess whether the locations of actions in the generated videos are accurate. Section Summary. In this section, we evaluate 8 video generative models on our benchmark, noting their varying input requirements and capabilities, particularly highlighting that only VideoPoet and Lumiere can utilize multiple frames for conditioning. We introduce 4 metrics to assess physical understanding in generated videos, culminating in a Physics IQ score that reflects how accurately the models replicate real-world physics, with a focus on the spatial accuracy of actions through our spatial IOU metric. Section. Where and when does action happen? Spatiotemporal IOU. In this section, we explore how actions are evaluated in videos using various metrics. First, we introduce spatiotemporal intersection over union, IOU, which goes beyond spatial IOU by considering not just where an action happens, but also when it occurs. Instead of averaging over time like spatial IOU, spatiotemporal IOU compares motion mask videos frame by frame. We calculate it by taking the size of the intersection of the real and generated motion masks and dividing it by the size of their union. This metric helps us understand if a model accurately captures both the location and timing of actions. Next, we discuss weighted spatial IOU, which is similar to spatial IOU but adds a layer of detail by measuring how much action occurs at each location. Instead of just indicating whether an action happened, it distinguishes between different types of motion, like a pendulum's repeated movement versus a ball's single pass. We compute this by averaging the action across frames and then summing the minimum values of the 2 motion maps, divided by their maximum values. This gives us insight into both the location and intensity of actions. We also consider mean squared error, MSE, which calculates the average squared difference between corresponding pixels in 2 frames. This metric focuses on pixel-level accuracy, making it sensitive to visual details and interactions. For example, if a model alters object colors unrealistically, MSE will highlight this issue. While MSE is strict, it complements the other metrics, providing a well-rounded assessment of physical realism. Lastly, we evaluate visual realism using a multimodal large language model, MLLM, specifically Gemini 1.5 Pro. Instead of rating videos directly, we employ a 2 alternative force choice, 2AFC, method, where the MLLM is presented with pairs of real and generated videos and must identify the generated one. The accuracy of this identification is expressed as a percentage, with a chance rate of 50%. Higher accuracy indicates that the MLLM can distinguish generated videos, while scores near 50% suggest that the model has effectively created realistic videos. Further details on this evaluation are provided in the appendix. Section Summary. In this section, we introduce several metrics to evaluate video generation, including spatiotemporal IOU, which assesses both the location and timing of actions, and weighted spatial IOU, which measures the intensity of actions at specific locations. We also discuss mean squared error, MSE, for pixel-level fidelity and a multimodal large language model, MLLM, evaluation to gauge the visual realism of generated videos through a two-alternative forced choice method. Section: Physical Understanding. In this section, we aim to understand and measure whether generative video models grasp physical principles through our Physics IQ benchmark. We evaluate all 8 models in our study across various scenarios and camera positions, left, center, and right, using our benchmark dataset. The results are illustrated in a figure showing our dataset qualitatively. We first present the overall Physics IQ results, which include metrics related to physical understanding, such as spatial intersection over union, spatiotemporal intersection over union, weighted spatial intersection over union, and mean squared error. The key takeaway from the left side of the figure is that all models fall significantly short of the physical variance baseline, with the top model achieving only 24.1% of the maximum score of 100%. Each scenario was recorded twice to capture natural variability in real-world physical phenomena, which we refer to as physical variance. The figure is normalized so that pairs of real videos differing only by physical randomness score 100%. The gap between model performance and real videos highlights a serious lack of physical understanding in current generative video models. Among the models, VideoPoet, Multiframe, ranks the highest, and it is noteworthy that VideoPoet is a causal model. For the 2 models that have both image-to-video and multiframe versions, the multiframe versions perform better, which aligns with our expectation that having access to temporal information aids in predicting future events, as required by our challenging benchmark. When we delve deeper into the results, we break down model performance into categories like solid mechanics, fluid dynamics, optics, thermodynamics, and magnetism. No category is fully solved, but performance varies, with some categories showing more promise than others. All models perform significantly better on spatial intersection over union, which only considers where an action occurs, rather than when or how much action takes place. Even a simple metric like mean squared error reveals a large gap between realistic videos and model-generated predictions. We report each model's performance on individual metrics, confirming that VideoPoet, Multiframe, excels in most metrics, while stable video diffusion leads in weighted spatial intersection over union. However, stable video diffusion struggles with object placement and dynamics, as seen in its weaker scores for spatial and spatiotemporal metrics, which is also evident in the generated videos that often display exaggerated and implausible movements. Similarly, Sora performs well in weighted spatial intersection over union but lags in other metrics. The videos produced by Sora are often visually appealing but frequently include transition cuts, which are penalized by several metrics. We believe that if a future version of Sora adheres more closely to the prompt, its Physics IQ score could improve significantly. We visualize the best and worst performing scenarios for the highest and lowest ranked models, showcasing both instances of physical understanding and failures. Next, we explore visual realism. Our findings reveal a notable lack of physical understanding in current generative video models. To quantify the visual realism of these models, we asked a capable multimodal large language model, Gemini 1.5 Pro, to identify the generated video from pairs for each scenario in the Physics IQ benchmark. The results are shown in a figure comparing realism and understanding. The multimodal large language model score reflects how well a model can create videos that deceive it into classifying them as real. Scores closer to chance performance indicate that the model struggles to distinguish between real and generated videos, suggesting high visual realism. Overall, the multimodal large language model often identifies the model-generated video accurately, with Lumiere Multiframe achieving up to 86.9% accuracy. Notably, Sora stands out with the highest score of 55.6%, significantly outperforming other models. Runway Gen 3 and Video Poet, Multiframe, follow, but with a considerable gap behind Sora. This indicates that capable models like Sora can generate visually realistic videos, despite their limited understanding of physical principles, as shown earlier. Importantly, there is no significant correlation between visual realism and physical understanding, highlighting the distinction between creating realistic videos and comprehending the physical principles of reality. Section Summary. In this section, we evaluate the physical understanding of generative video models using the Physics IQ benchmark, revealing a significant gap between model performance and real-world physical variance, with the best model scoring only 24.1%. Despite some models, like Sora, achieving high visual realism, our findings indicate no correlation between visual quality and physical comprehension, highlighting the limitations of current models in understanding physical principles. Section: Do video models learn physical principles? In this section, we explore whether video generative models that create realistic videos also understand the physical principles of our world. Our findings indicate that they do not. All models we evaluated lack a deep grasp of physics. The top-performing model, Video Poet, Multiframe, scored only 24.1 out of a possible 100, which is based on the natural variability seen in real videos. However, this does not rule out the possibility that future models could improve their understanding through next-frame prediction. It remains uncertain if simply enhancing the current approach will suffice or if we need different, more interactive training methods. Given the success of scaling and deep learning, we are hopeful that predicting future frames could lead to better physical understanding. While predicting pixels to learn physics seems tough, language models have successfully learned grammar from text prediction alone. We also noted that even though the models often struggled to produce physically plausible sequences, many still performed well in certain situations. For instance, Video Poet, Multiframe, accurately simulated paint smearing on glass, while lower-ranking models made basic errors, like objects passing through each other. Other studies have shown that with a sufficiently large dataset, video models can learn specific physical laws. We believe that as models are trained on larger and more varied video collections, their understanding of real-world physics will improve. We aim to track this progress by open-sourcing the Physics IQ benchmark. We found a significant gap between visual realism and physical understanding. These two aspects are not strongly correlated. For example, in a scenario where a burning matchstick is lowered into water, one model generated a continuation where a candle appeared and was lit by the match, despite the sequence being physically impossible. This tendency to create unrealistic objects is a common issue in generative models. In our tests, all models exhibited hallucinations, but stronger models like Runway Gen 3 and Sora often produced hallucinations that were at least relevant to the scenario, indicating some level of understanding. We also observed that most models consistently generated videos that matched the provided scene and viewpoint. Models like Sora and Runway Gen 3 excelled at maintaining consistency in object placement and attributes. However, we noticed biases in their outputs based on their training data. For instance, when given a video of a red pool table, one model quickly changed it to green, reflecting a bias towards more common green pool tables. Similarly, Sora often included transition cuts, suggesting a training focus on artistic video generation. Regarding metrics, popular methods for assessing video quality include PSNR, FVD, LPIPS, and SSIM. However, creating metrics that accurately measure physical understanding is challenging. We proposed a set of metrics to evaluate spatial, temporal, and perceptual coherence in video models. While none of these metrics are perfect on their own, together with the Physics IQ score, they provide a comprehensive view of model strengths and weaknesses. Importantly, these metrics do not directly measure physical phenomena but serve as proxies. For example, the MLLM metric assesses how much generated videos can mislead a multimodal model, but its effectiveness is limited by the model's capabilities. We found that while the MLLM could often identify generated videos, its reasoning was frequently incorrect. Additionally, we noted that stable video diffusion produced many hallucinations and unrealistic object movements, yet it performed well on certain metrics. This highlights the importance of not evaluating metrics in isolation. For instance, Runway Gen 3 excelled in spatial action location but struggled with temporal consistency. We designed the Physics IQ benchmark to be challenging to provide valuable insights for future model development. Our metrics may be conservative, penalizing object hallucinations and unwanted camera movements, which some models, like Sora, exhibited more frequently. While this may not be ideal, we believe that in a field where hype is prevalent, scientific benchmarks should prioritize caution.